In this section, we're going to look at probability distributions that come from continuous random variables. So instead of looking at discrete probability distributions, we're going to be looking at continuous ones. And one difference is that when we were finding discrete probabilities, we were counting how many times something could happen and dividing by the total. And so our discrete probability distribution, it looked like a histogram with usually some finite number of bars. But a difference now is that when we're looking at continuous distributions, our distributions are going to be curves. And so we're going to be looking at probabilities of a range of values instead of just a specific value, because we have something continuous, there's an infinite number of possible values, and so the probability of any one specific value is going to be 0 in this case. And we're going to look at 3 or 4 continuous probability distributions and look at situations where they're helpful. And so there are 3 shown here. There's the normal probability distribution, the exponential probability distribution, and the uniform probability distribution. So the normal probability distribution is this symmetric bell curve that's shown on the top left. And the exponential distribution is this curve where small values are more common than bigger values. And a uniform distribution is where we have some interval and anything in that interval has the same probability of happening. Or let me say this, that the distribution is constant over this interval. And then we also are going to talk a little bit about something called the triangular probability distribution. And so this is where we have some sort of triangular curve like this picture right here. And so we're going to start talking about the normal distribution. And this is something that you've seen in previous courses, but I think it's good to review. And so the shape of this normal distribution is given by this curve right here that you don't need to worry about the formula. But the point is that there are 2 parameters in this function that control the shape. There's the mean, mu, and the standard deviation, sigma. And we want to take a look at how changing those values changes the shape of the distribution. Again, you don't need to worry about memorizing this formula or anything. We're going to have other tools, but it's good to understand what this function is. So here is this curve, and A is the standard deviation, and B is the mean here. And so if I change the mean, that changes where this curve is centered. So if I make the mean 5, this will be centered around 5, symmetric around 5. And if I change the standard deviation, that changes how flat or how spread out the curve is. So the standard deviation is telling us kind of on average how far from the mean values are. So if I make the standard deviation bigger, this curve becomes kind of flatter and wider, and on average things are farther from the mean. Whereas if I make it smaller, it becomes skinnier and stuff gets closer to the mean. And in Excel, we can find probabilities associated with the normal distribution using this Excel command norm.dist. And if we have a standard normal where the mean is 0 and the standard deviation is 1, so there, a standard normal you can think about like z values, then you can use this norm.s.dist command. And so I want us to practice using this a little bit to get some review. And so in exercise 1, we have a random variable that follows the normal probability distribution, and we have a mean of 80 and a standard deviation of 20. And we want to use Excel to find some probabilities. So in part A, it says, what's the probability that a randomly selected value from this population is less than 1/12? So here we have our little curve, our symmetric bell-shaped curve, and our mean, our value in the middle, is 80, and we want to find the probability that x is less than 1/12. So we want the area to the left of 1/12. And so in Excel, we could do equals norm.dist, and we could plug in 1/12, and then we could put the mean and the standard deviation, and we could put true or 1 for cumulative. And this will give us that area to the left of 1/12, and this is about 0.9452. You could instead convert or find the z-score for 1/12, and then this would be a standard normal, and you could use the norm.s command, and that would also give you this same value. Now let's look at part B. Here we want the probability that we get something that's more than 95. So if we draw our picture here, again we have 80 in the middle, and 95 is to the right of that, and this probability would be the area to the right of 95. Well, if I do norm.dist of 95 and put in the mean and standard deviation and true, that would give me the area to the left of 95, which isn't what I want here. But the area to the left and the right should add up to 1. And so if I want the area to the right, what I could do is 1 minus the area to the left. And so if I plug this into Excel, this would be about 0.2266, and that would be that area to the right. If instead of just an area to the right or the left, if I wanted the area between two numbers, so in part C, I want the area between 50 and 60. Well, let's see, I want the area between 50 and 60. If I took the total area to the left of 60, I could calculate that by doing norm.dist and plugging in 60, and then plugging in the mean and standard deviation. But that would give me the total area to the left. I don't want the total area to the left. I just want the part between 50 and 60. And so what I want to do is I want to subtract the area to the left of 50. Well, that is norm.dist when I plug in 50. And so I could plug in 50, plug in the mean and standard deviation, and if I subtract that area to the left of 50, this will give me the area between both of these. And I'm running out of room here, but this would be about 0.0918. This would be the area between those two values. So this is great. Now we know how to find probabilities for the normal distribution. But another thing we might want to do is maybe we know something about the probability, and we might want to find the x value that satisfies that probability. And so this would be like working backwards. And we could also find probabilities using tables. We did it here using Excel. And so if we were using a table, we'd have to be backtracking and trying to figure out what we would have started with. But in Excel, we can use the same kind of formula that we did before, except we're going to replace the dist with an inv or inv for inverse, which means we're doing the opposite that we were doing before. So in exercise 2, it says we have a random variable that follows the normal probability distribution with a mean of 50 and a standard deviation of 20. And part A asks for the value of x that represents the 75th percentile. So we have this curve, and we have 50 in the middle, and we want to find the value of x. We want to figure out x that has 75% of stuff to the left of it. So to do this, what we could do in Excel is we could do norm.dist Now we're going to have INV instead of .dist, and I'm going to plug in the total area to the left of the x that I'm looking for. So here I would plug in 0.75. And then I need to tell Excel again what the mean and standard deviation are. But if I plug this in, this will tell me the x value that has an area of 0.75 to the left of it. So that tells me that this 75th percentile is 63.49. In part B, we want to do the same sort of thing, except now we want the x that has 40% of the data to the left of it, or a probability of 40% below it. So that means my x is going to be somewhere on the left of center, and my area to the left is going to be 0.4. So here I would do norm.inv, and now I would plug in 0.4 and my mean and standard deviation, and that will give me the x value that has 40% below it. And if we think about this, since this is 40% to the left, it should be somewhere to the left of the middle, and the middle is the mean of 50, and so we would expect an x value that's a bit smaller than 50 here. And sure enough, this turns out to be about 44.9. In part C, now it's asking for the value of x that represents the highest 10%. So here, this is saying, well, I want to find the x that has 10% to the right. Well, if it has 10% to the right, that means there must be 90% to the left. And so here we could do norm.inv of 0.9 and the mean and standard deviation. And this would tell us that that highest 10%, that x value is about 75.6. And so here we knew something about the probability and we wanted to find an x value. Now let's see how we could use these tools to do a more real-world example. In exercise 3, it says, according to the IRS, the Internal Revenue Service, the average income tax refund for the 2009 tax year was $3,114. And it says, assume the refund per person follows the normal probability distribution and that the standard deviation is $988. And so part A asks for the probability that a randomly selected tax refund from the 2009 tax year will be more than $2,300. So here, more than means that we're looking for an area to the right. We know an x value and we're looking for an area to the right. So here we could do 1 minus the area to the left of 2,300. And then we could plug in the mean and standard deviation and put true. And this would give us the probability, which would be about 0.795. And so this might help the IRS make decisions to see if someone had a really big tax refund, to maybe better understand the probability that that happened. Maybe they could use this to make decisions about who they audit or things like that. Part B asks for the probability that a tax refund is less than $1,600. So that would be looking for an area to the left. So here we could do norm.dist of 1,600 and plug in our mean and standard deviation, and that would give us, oh, and we need true at the end, that would give us the area to the left of this value. And this is about 0.06. So this would tell us there's about a 6% chance of having a tax refund that was less than $1,600. And so next, maybe try parts C and D, the solutions are on Canvas, and see if you can use all of these tools to try to find the probability that a randomly selected tax refund is between two values, and to find the refund amount that represents the 75th percentile of tax returns. And below this, we have a picture that reminds us for a normal distribution, again, we have the mean in the middle. And then if I go out by 1 standard deviation, I have about 68% of my data in that interval. If I go out by 2 standard deviations, I have about 95%. If I go out by 3, I have 99.7. And so this tells me if I know that a certain value is, let's say 5 standard deviations away from the mean, that tells me it's super unlikely that that will happen. And so if I'm, for the example, if I'm the IRS and someone has a tax return that has a z-value of 5, that would tell me, ooh, that was really far away from the mean. That's really unlikely to happen. Maybe it would be worth looking into people who are maybe more than 3 or 4 standard deviations away from the mean. And so normal distributions are really nice because we have all of these tools to understand, find values, and a lot of things are normally distributed. Some other distributions we'll talk about next are the exponential distribution and the uniform distribution. And we'll see when those might be helpful and how we can calculate probabilities for those.